Hi everyone, today we are going to look at the rules of exponents, and this is in your pre-algebra course. This is lessons 1.02 and 1.03. The first thing we want to do is we want to look at the different rules that we see with exponents. So these I would definitely write in your notes. Everything I'm writing on the board here I would write in your notes so you have them. The first rule that we want to talk about with exponents is the product rule. So if we look at the product rule, what the product rule is telling us is it's telling us that if we have the same base, so if you have the same base and you're multiplying, that's what product means. I'd be writing this down. And you're multiplying, you add your powers. So if you have the same base and you're multiplying, you want to add your powers. So that tells us that if we look at that first example here, the first example says 4 to the third times 4 to the second. The first thing we should notice is we should notice that this is a 4 and this is a 4. That's our base. So this rule tells us that if the base is the same and we're multiplying, in this case that's what this is, a multiplication symbol, then we keep our base, so we keep the 4, and we take our powers and we add them. So we would do 3 plus 2 and get 5. So our answer would just be 4 to the 5th power. Now the reason that works is because if I were to actually write this out in standard form, 4 to the third is the same thing as 4 times 4 times 4. That's what 4 to the third tells us. And then if we have another 4 to the second right here, that would be the same thing as just doing another 4 and 4. And so what that gives us, if we look, is that gives us 1, 2, 3, 4, and 5 fours, which is what we put as our answer. So you can always write it out the long way if you'd like, but once we start seeing bigger numbers, we want to know our rules. So let's take a look at our second example there. The second example says 5 to the second times 3 to the fourth times 5 to the fourth. So in my mind, what I'm thinking is I'm saying, okay, what has the same base? Because I can tell that I'm multiplying here in all of these examples. And I know that if I'm multiplying, I have to look for things that have the same base. So if I look, the 5 to the second and 5 to the fourth have the same base. So that means that I can take these two powers and I can add them. So 4 plus 2 is 6. So this gives me 5 to the 6th power. And then I have times 3 to the 4th. Now I can't do anything else. This is my answer because they don't have the same base. So I could find out my answer and do 5 times 5 times 5 times 5 times 5 times 5 6 times, and then multiply that by 3 times 3 times 3 times 3 4 times. But in terms of simplifying it, that's as far as I need to go. So that's what the product rule tells us. It tells us if they have the same base and we're multiplying, all we have to do is add our powers. Now, if we switch over to quotient rule, quotient is a fancy word for the answer to a division problem. So the quotient rule tells us that if we have exponents with the same base, so exponents with the same base, and we're dividing, you want to, and instead of add our powers, you actually want to divide or subtract. Subtract our powers. So let's look at a couple of examples for that one. We have 5 to the 12th divided by 5 to the third. Again, a couple things you should be looking at. First thing you should be looking at is it has a fraction bar, and the fraction bar means to divide. The other thing you should be looking at is they have the same base, which is a 5, because they have to have the same base. So we don't actually do anything with the 5, we just keep that as part of our answer. And then we do 12 minus 3, which is 9. And so that's all we would have, 5 to the 9th. If we look at the second example, it says 5 to the third times 4 to the 13th, all over 5 to the 2nd times 4 to the 12th. In this example, we can't put the 5 and the 4 together. They're different bases. But what we can do is we can actually look and we can see, we can break it up into two little sections here, and both of those are being divided, or there's a fraction bar. So if I do 5 to the 3rd divided by 5 to the 2nd, remember I keep my base, and since I'm dividing, I just take my powers and I subtract them. So I do 3 minus 2, which is 1. And then I'm going to do the same thing with my 4s. So then I have a times 4. And then if I do 13 subtracted by 12, that leaves us with a 1. So our answer would be 5 to the 1st times 4 to the 1st. And remember, 5 to the 1st times 4 to the 1st is the same thing as 5 times 4. And we could even put that's the same thing as just 20. Okay, we have a couple more rules we want to look at. The next rule we want to talk about is called the power to a power rule. And the power to a power rule is something that's similar. If you look at these examples, it looks like this. And it basically says that if you have a base raised to a power, and then raised to another power, you multiply those powers. You multiply them. Okay, you multiply. So this looks like oftentimes a to the m, and then you have the n out there. And that would be the same thing as a to the m times n, which can be a little confusing. So we'll take a look at our examples there. So if we have 5 to the 4th raised to the 2nd, what that's telling us is that's telling us we need to, it's almost like we're distributing the 2 to this exponent. So we're multiplying these together. We have to multiply. So that would be 4 times 2, which is 8. So we would have 5, that's our base, raised to the 8th power. So that would be our answer. Now if we look at the next example, the next example says 3 to the 3rd times 6 to the 3rd raised to the 2nd. And when we look here, I always deal with parentheses first. So I'm looking at this, this section first. And again, it's almost like we're distributing our power. So we have a power raised to another power, which means we multiply those. So if we multiply those, we get 3 times 2, which is 6. So I leave my base, and then I bring my 6. And then I'm multiplying that by 3 to the 3rd. Now again, I can't use the product rule, which is what I just learned earlier, because this has a base of 3 and this has a base of 6. So this is actually as far as we can go. Now the zero rule is probably the easiest. So anything raised to the 0 power, anything, it doesn't matter what it is, anything raised to the 0 power is 1. Okay, anything, anything, anything. So again, if you look at our examples, we have 100 raised to the 0 power, that's just going to be 1. That's our answer. We have negative 400 raised to the 0 power. Again, that's just going to be 1. So anything raised to the 0 power will always be 1. Okay, the last rule we're going to look at today is called negative powers. What do we do with negative powers? So anytime we have a negative power, we need to really switch it so that it's positive. So I'm going to give you kind of an example with variables, and then we'll look at examples. So if I have a raised to the negative m power, I need to write this as a fraction. So what I'm going to do is I'm actually going to bring this to the bottom, or to the denominator of my fraction bar. And when I do that, it becomes a positive m, and then I just put it over 1. So this is how I look at it, okay? So this is kind of how I'm looking at it. Here's an example. So EX means example. If I had 5 raised to the negative 2 power, I always think of this like a house. So this is 5 to the negative 2, or negative 2nd power. And the reason I think of it as a house is because if I see a negative power, here's my fraction bar, I have upstairs and downstairs on my house. And if it's not happy upstairs, then I need to move it downstairs. So I'm going to make it 5 to the 2nd. And when I move it, it becomes happy, so it's no longer negative, it's actually positive. and then I just put a 1 on top. So our answer would be 1 over 5 to the second. And we know that 1 over 5 to the second, if we wanted to keep working that out, would be like 1 over 5 times 5. Which again, if we wanted to work that out, is like 1 over 25. So all of these mean the same thing. All 4 of these statements, this one, this one, this one, and this one, they all are saying the same thing. Okay, let's do another example. Let's say I had something like 3 over 4 to the negative 3. Again, anytime I see a negative power, I have to think about moving it. So we didn't talk about this. If the power is in the bottom and it's negative, well, again, we think of our house. If it's negative, it's not happy on the bottom. We now have to move it to the top. So here's going to draw my fraction bar for upstairs and downstairs. I'm going to take this 4 to the negative 3. If it's not happy, I'm going to bring it up. And when I do, it becomes positive. Now what I look at here is this is just a 3. And remember, anytime you have a number that doesn't have a power, you can actually make it have a power. It's just a 1. It's just a hidden 1. So anytime you don't have a power, you just make it a hidden 1. And that's happy. That's fine. There's nothing wrong with that number. So that really needs to stay on top. So I'm going to make that 3 to the first on top. So it's almost like you're multiplying those together. Now what's happened is there's nothing left in the bottom, and that's completely fine. That would just be like a 1. So this would be like 3 to the first times 4 to the third. Let's practice a couple of questions together. The first one says, if 4 to the second power raised to p, the variable p, equals 7 to the 16th power, what is the value of p? So for this one, and again, feel free to pause the screen if you want to write these in your notes. I would write these in your notes. They're going to be similar to this on your test. And I made a mistake. So this should actually say, I'm sorry, 4 to the second and then 4 to the 16th. Let me change that real quick, because then we wouldn't be able to solve it unless it's this. There we go. So if this is equal, what we can see is they have the same base, which is a 4. The other thing we can see is that we have kind of a distributive property going on here. It's like 2 times p. And we know those two powers, 2 times p is 2p, should be equal to the power on this side, which is 16, because we want them to be equal to each other. So since they both have 4 as our exponent base, we know we can set the powers equal to each other. And we can solve this by saying 2 times what gives me 16? And that would be 8. So for this problem, all we would have to do is plug in an 8 for p, and then we would see that both sides are in fact equal. Okay, we're going to shift over here to this one. It says, what is a to the x times a to the y? First thing we need to recognize here is that they have the same base, which is an a. So the next thing we want to do is if we notice they have the same base, we want to see what they're doing, and in this case they're being multiplied together, which tells us that we have to add our powers. So this is the same thing as a raised to the x plus y. And this answer is just variables. That's just testing that you know the rules. So it would stay just like that. The third question says simplify 6 to the 5th times, and then in parentheses, 7 squared raised to the 3rd, all over 6 to the 7th. So this one's tricky. We're actually going to do a couple of things there to solve it, because we have a couple of rules that we're using. The first thing I would do is I would pretend like the bottom fraction's really not there yet, and I would just look at the top. And when I look at the top, I can't do anything with the 6 to the 5th, but I can distribute this 3, and I can make this 7 to the 6th, because when I distribute, that's like multiplication. So I multiply our powers. And then on the bottom, I have 6 to the 7th. So I've kind of taken care of those parentheses in the numerator. And then from here, what I'm going to do is I'm going to see what else I can do. So I see there's a fraction bar, which means to divide. And I see that there's a 6 to the 5th and then a 6. And I know, let's see, there we go, that I need to divide those. So if it's actually 6 to the 7th, let me make this a different line here. So when I do that, when I'm dividing, I have to take my powers and subtract them. So this would be like 5 minus 7. And 5 minus 7 is negative 2. Negative 2. So this is the same thing as 6 to the negative 2 power times 7 to the 6th power. That's what it simplifies to. Now we know we don't like having negative powers, so we can rewrite that in fraction form, kind of like our house. We have an upstairs and a downstairs. If it's negative, it's not happy, so we need to bring that down. But the 7 to the 6 is happy, it's positive, so we're going to leave that up. So any of these are equivalent to each other, this answer, and then again this last answer. That one's a little tricky, so you may want to rewind it and listen to that again, or just take a look at that. Okay, this practice question says 8 to the 4th to the 0 power times 7 to the negative 5 times 7 to the 2nd. So first thing I always do is get rid of these parentheses. And I know I can multiply this. This is power to a power rule, which would give me 0. But I don't really have to do that because I know anything raised to the 0 power is 1. So that actually cancels. So I'm just going to get rid of that. So it's one less thing to worry about. And I'm actually going to just combine these two. And again, when we're multiplying, we add our powers. So this would be like negative 5 plus 2. And negative 5 plus 2 is the same thing as negative 3. So I have 7 raised to the negative 3 power. Now, we know if it has negative power, we need to change it as a fraction bar. We know that this is not happy, so it has to go to the bottom or the denominator of our fraction bar. And when we change that, the negative goes away because we've moved it. And then we just put it over 1. And so it's 1 over 7 to the 3rd power. All right, guys, this is the last one we have for this lesson. This is actually a freebie test question. So your test question on your test will look exactly like this one, except it might have different numbers. So we want to solve this. We want to put our answer in simplified form. We want to show all of our work. So this one's a little complicated because there's really a lot going on here. So go ahead and write this question down. I'm going to rewrite it over here so I have more space. Okay, and I'm going to do piece by piece. So I'm actually going to look at just this section first, and I'm going to simplify that first. So I'm just going to write that first so I don't get overwhelmed. So the first thing I'm going to do is I'm going to take my power here, and I'm going to multiply it like a distributive property to everything inside that parentheses. And when I do that, I get 2 to the negative 16 power, because 8 times negative 2 is negative 16. Times 5. Again, I'm doing negative 5 times negative 2, which is a positive 10. Times, and then this one here, we could do 0 times negative 2, but we're just going to get 19 raised to the 0 power. And really, we know anything raised to the 0 power is just 1. So I'm actually not even going to write this because we know 1 times anything is just itself. So this actually cancels, it just becomes a 1. So that whole thing, when I distribute that negative 2, is 2 to the negative 16 times 5 to the 10. So that little portion is done. And the next section is the next one. So I'm going to write that one down. So 5 to the negative 2, 2 to the 3rd, all over, or raised to the 4th. And from here, when I solve it again, I'm going to distribute those powers. So I'm going to distribute those powers. So that's going to give me 5 to the negative 8, so it's negative 2 times 4, all over 2, and this is 3 times 4, which is 12. It's just multiplying those powers. Multiplying those powers. And then I'm just going to write the last one down, which is 2 to the 28th. So that's what we have so far. We have 2 to the negative 16 times 5 to the 10th times 5 to the negative 8th, all over 212 to the 12th times 2 to the 28th. Pretty lengthy still. It's a tough question. So let me write this out so it looks pretty. So we're actually multiplying like all of this together, and it looks kind of chaotic right now. So I'm going to write it out. So this would be like 2 to the negative 16, 5 to the 10th. Remember, we're multiplying all this, times 5 to the negative 8. We can kind of jumble it all together. 2 to the 28th. And the only denominator we have that shows is 2 to the 12th. So I'm just going to put it all over 2 to the 12th. We can do that because it's really like all of these are over a 1. And if we were to multiply all those fractions together, we would multiply the denominators, which would make it a 1. Okay, now from here, what we're going to do, what we notice is we can combine again, combine what we see. So when I look at this, I see I have a 2 to the negative 16 on the top, and I have 2 to the 28 on the top. So if I combine my powers for anything that has the same base, that would give me 2, and it would be like negative 16 plus 28. And if I do negative 16 plus 28, I actually get 2 raised to the 12th power. So that's on the top of my denominator, my numerator. And then I'm going to put the next two together, which is 5 to the 10th times 5 to the negative 8. They have the same base of 5. And if I combine those, that's like 10 and negative 8, which is actually a 2. And then I look and I only have 2 to the 12th in the denominator as well. So when I look here, what I've got, once I've done all that work, is I've got 2 to the 12th times 5 to the 2nd all over 2 to the 12th. Now my last step is to see, when I divide, can I get rid of anything? And remember, anytime you have the same base and you're dividing, which are these two, you subtract your powers. So if we have 2 to the 12th divided by 2 to the 12th, that's really like 2 to the 0, because 12 minus 12 is 0. And we know anything raised to the 0 is 1. So they really cancel each other out, and you are just left with 5 to the 2nd as your answer. So on the test question, it asks you to write your answer in simplified form, which is 5 to the 2nd. It's also just 25, so you could just put 25 because 5 times 5 is 25. And that would be your answer.